Right, looks like Natalie is here.
Hi, everybody. Sorry for the delay. My internet kicked me out. So now I have my iPad as internet source. So let's hope and keep fingers crossed the iPad stays stable. But just in case, I also send my presentation to the iPad. So worst case scenario I had there. So boss, Erin, do you have some announcements or shall I start?
Let me see. I don't think for the management team, no meeting on Monday because we're all going to be on airplanes for the most part. Everyone have a wonderful Thanksgiving. And I think that's it. Actually,
Okie dokes.
Yes, I guess one more thing. As a reminder, if you do not have the all hands meeting blocked on your calendar, please make sure you get that blocked. We're waiting for RII to not be on vacation for an entire week so that they can tell us we can spend our money. But we should have the block of hotels hopefully reserved by next week. And then you guys can all go ahead and make your arrangements, etc. So I'm assuming Jen will be sending out an email with regards to that next week.
I will. I'll be sending out an email with the link. There's going to be a link that you just click on.
Yes, it's January 22nd through the 24th.
Good. In my calendar.
Yep. Okay.
Okie doke. So again, yeah, let's see if my internet holds. They were doing roofing, so ever since it's spotty. Anyway, let's share screen. Et voilà. Specs. Oh, voila. And let's make that small. Can everybody see my slides?
Yep.
Looks good.
Yep.
Great. So far, so good then. So I was tasked to talk a bit about Thrust 1 and in particular, transport. So Thrust 1 is really about hybrid electrical ionic charge transport. And my slides don't move. Next, let's see. And just as a reminder, so one key goal of Thrust 1 is really to control ion and polar transport and storage processes. And if you look at the individual objectives, and I have to say thanks to Chet, who made actually the template for those Thrust 1 slides, and I nicely used them. So Thrust 1's objectives are really about the physical structure of polymer electrolyte interfaces, structure property relations, as well as quantify strengths of ion polar interactions. And today I really want to focus on transport processes, really highlighting previous work from my group and what has been done and how we can build on it. And the same with electrical ionic transport, which can be obviously more challenging because now we deal not only with electrons and holes, but also ionic species. And this is really what I like in the graph that Specs used. I assume was from my Obadiah. We start to have a mess because we have polymers, we have electrolytes, we have charges, we have ions, etc. And we really try to fundamentally understand how they are correlated. So how can we really control and assess charge transport? As mentioned, I will in particular focus on control. Alberto really addressed some of the in situ methodologies to assess charge transport in his presentation a while back. And I really like to take you a bit to across a journey, also my scientific journey. I guess that happens when you get older. How we can manipulate charge transport. And actually a lot of these things then also go a bit into Thrust 3 where it goes about durability. So very early on, and for those who don't know, I'm a trained material scientist. So we like polyethylene. It's a commodity polymer that is used everywhere. I know it got maybe a bit of a bad reputation because of pollution of our world, but I have to say polyethylene, I'm an advocate for polyethylene straws, so easy to produce, and actually it's really the people who throw it away that actually pollute. So why would we mix a semiconductor? And here we still, I apologize to the chemists, worked with P3HT, possibly the fruit fly for the first generation of semiconductor. Pardon? So it's a conjugated polymer. What is nice, it's still a flexible chain polymer for those who have seen me talking about rigid rod versus flexible chain. So they're very similar, the way they crystallize, how we can process, etc. And one reason actually to blend those at that time was to make them actually mechanically robust. While often the field is called flexible electronics or flexible energy harvesting, many of our semiconductors are actually not flexible, they're not plastically deformable. So therefore, we have to add something like polyethylene. And just to bring in some material science, you can easily test toughness, so how much energy a material can absorb from tensile tests. So you stretch, you measure the elongation, and you essentially measure at what stress does the material break. And here you see if you take polystyrene and PMMA is plexiglass, and P3HT of a medium molecular weight, they really break very early, not only with respect to elongation, but also the stress. And you see P3HT really breaks super early at a very low stress. And this only gets worse if you go from P3HT to PBTTT to N2200. But once you make the blends, you immediately see something. We can increase the strength where deformation starts to occur. That's actually this maximum after the linear behavior. And then you can actually elongate it very similar like polyethylene. And the toughness is actually, for those who want to know, given by the area underneath the mechanic between the stress strain curve. Clearly, we add an insulator. So what about the electronic properties? And during my lifetime, Alberto's group, of course, has now much more sophisticated methodologies. We simply made field effect transistors. So a field effect transistor is a 3-terminal device, which simply means you have a source, a drain, electrode, here in red. At that time, you often had a common gate, so that's the 3rd electrode, and between you sandwich a semiconductor in blue and an insulator. Why do you need 3 terminals, so 3 electrodes? You first apply the gate bias here, so across your sandwich structure, and that means you polarize the insulator and you get actually charges at the interface from the insulator to the semiconductor. And those charges then you manipulate with the source drain bias. And that gives you then a bit of you get the mobility out as a parameter. So how easy can charges move? We added 3 different types of polyethylenes: linear density, linear low density. So they have some branches, and ultra low density, which is not a linear polymer anymore. It's more like this mess where the branches start to be as long as the backbone. And when we extracted the mobility from these transistor measurements, you see when you get the mobility of the P3HT here on the right and add polyethylene, we could really add a lot of polyethylene, 99%, and still have the same mobility. And when we used a bit less ordered, so more amorphous materials, we still had a pretty good threshold of 90%. And actually, maybe just in case, I see I'm talking, but Erin, in case I'm kicked out, maybe send me a text message. Not that I will talk 45 minutes and there's nobody there. Anyway, So here you see already we can actually blend and get good electronic performance, but also toughness. But I have to say, and I think that's really important for specs, it's as soon as you go to multi-component systems, you always have to be very careful how you process. I mean, either you just do a trial approach and make 200 different samples and see what works. We cannot do that because often we don't have so much materials, and I'm sure the chemists in our network won't be happy. Or you try to learn how to process. One way we do it often is measuring the crystallization temperature in solution. So we measured the crystallization temperature of P3HT in a solvent. Here you see that P3HT has some polarity. So if you add a solvent, it can interact. And therefore, the more solvent you add, the P3HT will crystallize below room temperature. Polyethylene, though, is only carbon and hydrogen. So you see if you add a solvent, the crystallization temperature is just little reduced from 100 and something degrees C to around 75. Why is this important? If you just go and spin coat, which I anyway hate, I must say, you first have crystallization of polyethylene, and then the P3HT is supposed to crystallize in this sea of solid polyethylene. As you can imagine, this will not work, and you will not get good films, and definitely not good films of good electronic and mechanical properties. So what this phase diagram tells you is you should cast the solution at higher temperature so that the P3HT crystallizes first at this dot, and only afterwards the polyethylene. So this has multiple advantages. The P3HT can crystallize where it has still a lot of mobility, so molecular mobility now, not electronic, so high diffusion, because most of the polyethylene is still liquid. That helps the ordering. And then once the polyethylene starts to crystallize, it forms ferrolides. It really pushes these electronic pathways together. Ideally, of course, you actually would cast exactly at this temperature where both crystallize at the same temperature. That would guarantee you the finest phase separation. And I have to say, once you know how to process, it works for every system. So here we went for a charge transport material, so a material for transistors from McCulloch, which the chemists named DPP, this unit TT, so this fused thiophene ring T for a single thiophene. And there we looked actually at the neat material. It's in principle a very nice charge transport material, but you see once you expose it to air for 8 hours, this source current versus gate bias. Remember, when you apply gate bias, you polarize the material, the dielectric, you get more and more charges, and therefore you get a higher and higher drain current. You still can manipulate the current by 4 orders of magnitude, but for instance, this little bump here tells you that it was unintentionally doped, and also it doesn't really switch on fast. Now, when we made the polyethylene blend, you see air exposure doesn't do anything. We keep the really nice on to off current, and therefore we know we have very good charge transport. What we thought is this is not chemical degradation, because we could not see why adding of polyethylene should prevent chemical degradation. So we assumed it has to do with traps. So if you expose the neat material to air, you create traps, and therefore you essentially make your device slower. So we looked into detail. So here again, you see a 3-terminal device, common gate on the bottom, insulator, source drain, and then the semiconductor. And we looked at various blends from the neat DPP TTT, with blends adding up to 95 of 8% of polyethylene. And you immediately see And this was measured now in nitrogen. So therefore you see even the neat materials behaving pretty well. But what is nice to see, the more polyethylene you add, the closer the threshold voltage goes to 0, and that should be. So if you don't have gate bias on, you shouldn't have charges in your system, so your current should be low. And we plotted this threshold voltage, so where the device turns on, and you see that, the more polyethylene you have, the lower the threshold voltage. And that's actually very important if you want to integrate transistors into more difficult structures like ring oscillators. But also is observable, maybe not by eye, just looking at the transistor characteristics, you see the sub-threshold slope, so how fast the transistor switches on. So the slope of this part of the transistor curve, it goes down significantly by adding polyethylene. So a lower sub-threshold slope means it becomes steeper. And it's a minimum at 50% of polyethylene. So why is that important? You can actually relate the number of traps with this sub-threshold voltage using a very simple formula equation that Paul Blom uses all the time. And what is nice, all the other parameters are given. So based on the sub-threshold slope, we can actually calculate the number of traps, this NT. And what we see is we have a minimum at 58% polyethylene. So this means adding polyethylene to our semiconductor reduces traps. It's a bit paradox because those who come from the bulk commodity world, polyethylene is actually not, for instance, a good oxygen barrier. But we believe it helps because polyethylene is obviously very hydrophobic. So it will repulse water and moisture, and that seems already to be big enough to help reducing traps. And other evidence is found for that. For instance, you can stress your transistor. Clearly, we sometimes stress also. But what means stressing a transistor? It means you apply a gate bias over a long period of time. And what you see is for the neat TPTT, you start to really have a massive shift of threshold voltage. So every time you measure, actually the characteristics is different. To be fair, this is not only a problem of organics, it's actually really, really pronounced with silicon, amorphous silicon. Once we add to the polyethylene, you see this is much less reduced. And usually people believe bias stress comes when you have traps in your material. So this really indicates that indeed polyethylene helps to reduce traps in our system. More, and that's now a material that all of you should be familiar with. We have that one in specs, N2200. N2200 in transistors leads to N-type transistors, meaning transistors that move electrons around. And electron materials is really are often a bit when you actually expose them to air. And you see that how you gradually and rapidly decrease the transistor performance when you just have N2200 transistors, expose them to air, and after a few, well, here 8 hours, you see you have exactly the characteristics I showed with this characteristic bump indicating doping and a relatively low on-off ratio. Now, when you did actually adding polyethylene, this is hardly the case. So it's pretty well-behaved transistor. So again, adding an insulator not only helps with mechanical robustness, but really helps the durability of your material. What I also like to highlight here, because people always said, well, you have vertical phase separation, the P3HD or N2200 goes to the bottom, the polyethylene on top. here, contrary to the transistors we did with TPP, TTT, here we used a top electrode, so a common top electrode. This means the charges you create are actually here now on the top surface. So either when we blend with polyethylene, we get a very symmetric vertical phase separation where the material, the semiconductor, goes to both interfaces, which is usually unusual because the top interface when you make the film is very different to glass. So therefore, we looked at the bulk transport. So really, rather than having charges moving at the interface, really going through our films. And here, a very good method to measure that is time of flight photoconductivity measurement, where you essentially have a film, thick film, 5 micron. So these are measurements on 5 micron thick films. You shine light on top of your film, you create charges on top, and you measure the time here, the x-axis, till the charges reach the other interface. Polymers are always messy, so how do you see if they arrive? We see that when you start to have a kink in the current. So here you see, taking the slopes, we can indicate the arrival time. And what you immediately observe is, once you add the polyethylene, here only 28%, you get drastically improvement in the time that the charges need to get through the bulk, 5 microns. So that means the 80-20 blend contains or sustains much faster charge transport than the neat material. And this is even more drastic when you measure electrons. So the only difference is you use actually different electrodes in your measurement. So in the neat P3HD, we could not measure actually any arrival time, likely because of massive trapping. Once we do actually the blends, you see we get actually very good charge transport characteristics, unless we really go to high polyethylene content of 98%. And again, this starts to be important when we talk about robustness or durability, as we sometimes call it in specs. Here I have not our systems, but normal solar cells. You see from the donor acceptor blend we used, this is pretty old work. So we had P3HD as the donor, fullerene, a soluble fullerene acceptor, and then we added polyethylene. So here we have the current voltage characteristics, and let's just first compare the blend, so the P3HD, the binary PCBM with one of the ternaries. And clearly, what is immediately clear, adding polyethylene doesn't absorb light, you lose on current, like the short circuit current. So if you plot the short circuit current, the blend, and the ternary, well, doesn't really look so good for the ternary. But again, if you have the films of the same thickness, these systems absorb much less light. So we did then devices of that are much thicker, 500 nanometer, which is nice and easy to do once you add the insulator. And when we made films that had the same absorption as the blend, the binary, you see we actually got to the same JSC. And if we did that for all the different compositions, it turned out we can add up to like 50% of polyethylene and still have working solar cells, but now of mechanical robustness. So going now to, so I really think we can exploit this, hopefully, for specs, because I have to highlight here we really have extreme amounts of the insulator, but what we often use is other insulators like polystyrene of very high molecular weight. So very high molecular weight means like 1 million gram per mole up to 20 million gram per mole. And then you only need to add about 1 to 5 weight% with respect to your active material, not the solvent. and you have robustness, for instance, but in many cases also you get the benefit of stability with respect to charge trapping. Clearly, so far I only talk now about hole transport. So what about ion transport, which will be as important in specs as the electrons and holes? And again, I will bore you first with results we got on P3HT, or then actually for ion conduction, we worked with Olivier Dautel in France. We started to work copolymers where he just made a tiny, well, he did, obviously not me, change in the structure, adding here and then these hydroxyl groups to render the P3HT. Here we call it P3HTOH. You see in the next slides, we usually call them now P3HHT, to render the material a bit more polar, so to help ion uptake. And how do we measure that? Actually, I should have had a graph here. We measure the absorbance of the systems when they get exposed to aqueous sodium chloride solution. And we measure actually how the absorbance changes over time when you apply a voltage. So here you drag ions in. If you change the bias, you drag them out again. And what you see is the more alcohol groups, possibly not very surprisingly, you have in your system, the more ions you can absorb, and therefore you have more rapid oxidation. You see, you can get them out, but you have actually to go to a bit of a higher bias to really get all the ions out. So chemical modification can manipulate ion flow. Again, not surprising,
Natalie,
but using, yes?
Can you just explain the experiment a little more?
Okay, yeah, I'm sorry, because usually I have, so it's really photoelectrochemical spectroscopy. So you have a film, you measure the absorbance, and the film is exposed to electrolyte, and you apply a voltage, a bias across the system.
And the bias is to just kind of, it's a electrophoretic bias or redox. Is it enough to?
It's redox, yes, yes. And I apologize, I should have had the graph. It's redox. So you apply the bias, you get the ions in, and therefore actually you either oxidize or reduce the backbone.
I see.
Does that make sense?
Yeah.
So it's a measurement that John Reynolds always does. Maybe Erin can jump in, so she will use the right words.
Okay, no.
But it's really, you get the ions in to actually, in this case, oxidize, I think, the polymer. And then, of course, vice versa. You take the ions out again.
Thank you.
And based on the slope, you can see essentially, well, it's a bit of an assumption, of course. The slower it is, the slower the ions get to the backbone. So here you see when you have more alcohol groups, not surprisingly, upon application of the bias, you get the ions in and you can more rapidly oxidize the backbone. So it's a bit of an indirect measurement of ion flow.
Okay.
Actually, it is shown here. Okie doke. So here you see, actually, this is the schematic. So you shine light, you have the film, you have a reservoir with your electrolyte, you apply the bias, and then you see really what happens to the absorption. I should have brought this slide first. While you apply different bias. So here you apply positive bias. You see you have bleaching of your main absorption, but you get here the polaron band, and vice versa. If you stop applying the bias, it goes back, but you have to apply then negative bias to really actually get all ions out. And you can do that. This was actually now in an electrochemical transistor, which is very similar. So here we have essentially only a gate, one electrode. If you now also have a source and a drain, you can make electrochemical transistors and do exactly the same. So you apply bias up and down, and when you apply the gate bias, actually here it's the gate bias, you change the source drain bias, and if you cycle, because the material doesn't swell, I show that in the next slide, the material really behaves extremely well. So over 50 cycles, you see you can get ions in, ions out, ions in, ions out, and therefore you oxidize the polymer. This is very different to P-BSS, which is a material that I anyway hate, where you see that you really start to lose over the cycling current. And that's actually really shown here, how drastically actually the current changes when you do the cycling. And one reason is that you lose some of the PSS and other things. So it's a lot of issue actually here. It's the mechanical robustness. And it has to do with the volume change. And just to show here a similar example, so again, the P3HHT, we couldn't actually measure P.PSS. So this is quartz micro balance measurements where we measure the volume change. We compare it then not with P.PSS, but the glycolated, so the G2T, these are PBTTT polymer as we use in specs, but with glycolated side chains. And really the key graph here is where from the QMCD measurements, we get the mass uptake. And you immediately see the problem when you have glycolated systems, glycolated side chains, or I should actually say ethylene oxide to be in agreement with IUPAC. You have massive mass uptake, and that leads to failure. And as mentioned, this was nearly impossible to measure actually with P.PSS because the mass uptake was so drastic. And the nice thing is, actually, we measured that actually in Shahika's lab in KAUST. We can distinguish what mass uptake is contributed with water. So these are these dashed lines, or ions, these dashed dotted lines. And what you see is the difference between P3HT and the glycolated material is you still have a pretty good ion uptake, these two little curves down here. I hope you can follow my cursor. But the key difference is, and that leads to the stability, that you have much less water uptake. Was there a question? I heard some rumbling. All good? Okay, I assume that means all good. When you look though closely on the two systems, especially at early cycles, well, even later cycles, I should have put the circle actually here. One big problem of P3HHT is it's still drastically slower than P.PSS. So here you see you apply a gate bias, you can actually get the ions in, and you have a very rapid response. So the P3HHT, because of course it's less polar, is slower, and that can be a problem for certain devices. So we have stability, but we compromise actually with the response time of the, in this case, OECT. So being sort of a one-trick pony, we went on and said, well, let's blend again. This time we were a bit more creative maybe than just using polyethylene. Clearly that's still needs to be judged. So we used our HHTT, P3HHTT with some alcohol groups every now and then. And as a additive, we didn't use a block commodity polymer. We used actually a block copolymer. That's why we have here the B for block of P3HT and ethylene glycol block. So why did we pick this one? So while the P3HHT is somewhat polar, we really worried about compatibility if we add, let's say, polyethylene. With P3HT, we still could find co-solvents, but once you have stark differences, let's say, of your semiconductor and just your polar material, the commodity polymer like polyvinyl alcohol or polyethylene oxide, you start to have problems. So we used some hydrophilic groups to make this part, this monomer unit happy of the P3HHT, but also added a P3HT block to make the other unit here in P3HHT happy in this sense. We also thought if you don't dilute too much the additive and add actually an active whole conductor, that possibly will help to not limit charge transport, and here actually then the electronic charge transport, so the transport of holes. Now here you see similar characteristics as for normal transistors. So this is an organic electrochemical transistor where we plot the gate bias. Remember, in the normal transistor, the gate helped us to create charges at an interface. Here, it's simply the gate is an electrolyte and it drags the ions into the system. And therefore, the higher the gate bias, here negative, you get actually a current. You immediately see, though, a problem. And I have to say the community is often a bit cheating. They, many cases, do not give actually at what rate they measure, meaning at what rate do they change the gate bias. And if you go back here, you see if you go very slow with 0.01, you get actually a pretty decent characteristics where the forward and backward scan is sort of identical. However, if you go faster and faster, you see you get ions in, oxidizing your polymer, creating a current, but it's much more difficult to get ions out. So they're too slow. When you do now that with some of the block copolymer, so we added 25 weight%, you see we can even go super fast with 1 volt per second, and we still have essentially no hysteresis. So that tells us adding the block copolymer helps in getting the ions in as well as getting the ions out. And if you look at two key parameters, we already talked about the threshold voltage or the change in threshold voltage. Here really, like when you take the 0.251, it turns on here. But if you go back, the threshold, well, where it stops is actually the much higher gate bias. So this one really tells us about how pronounced the hysteresis is. So the larger the delta VT, the larger the hysteresis. And you see the faster you sweep the gate bias, the neat P3HHT copolymer with P3HT, the very rapidly over 1 order of magnitude, actually 2 orders of magnitude, you changed the threshold voltage. Versus it's pretty stable actually when you add the block copolymer. The other characteristic that is important is the transconductance. So it gives you really how easily do you have you change the current. And again, while at the beginning the neat material has a pretty decent transconductance, it goes to pot pretty fast once you actually scan fast, versus in the blend, it's actually pretty okay.
Natalie?
Moreover, if you do, yes? Yes?
Have you done a control where you actually don't use the block polymer, but you just blend with PEO?
Yes, we did, and I expected that question. I don't actually have the data. Only PEO itself actually also works. It's just much more difficult to get really homogeneous films. So the yield of well-behaving films is much lower. Also, if you do stability measurements, so you put your films into water, the block copolymer is actually helps to keep the device more stable, which makes sense because PO at the end will still swell and sometimes mechanically disintegrate, versus when you have the block copolymer, it helps simply because the P3HD will not be affected by aqueous environments.
Great, thanks.
But in principle, it's doable if you just want to have a nice transistor that simply doesn't operate for a long time. Does that make sense?
Yeah.
I have to say, though, I see options by going to very high molecular weight PO. Again, 1 million, 2 million. I believe that potentially could work, actually. But again, high ultra-molecular weight polymers, one has to know what one is doing when processing. But the blending definitely works. And if you look at this graph here, and I think that could eventually also be important for specs. I mean, it's different applications. If you change, when you look how the key parameter like transconductance works when you change transistor geometry. So here you have bigger devices versus smaller devices. In principle, in a real nice theoretical world, the geometry of the device should not matter. It should, again, also not matter with the rate that you measure, but you immediately see larger devices, which are actually easier to fabricate, obviously, than here. The smaller devices, you have to go to lithographic approaches. They do not scale, and you really have a large scattering of your data with measuring speed. Versus once you blend, and I really think that's important if you want to go further in engineering eventually, the devices scale extremely well, actually nearly too well for my taste, but it shows the blending makes the devices super well behaved, and it doesn't matter whether you have small or large devices. What you see here, and that's a bit the problem only going with polyethylene oxide, you lose a bit in that key parameter of organic electrochemical transistor, which is the product of mobility and capacitance. But I think it's still pretty good. And I'm sure with clever design of this block copolymer, this was at the end pretty random, actually, that we picked that one. We could, I'm sure, get actually this mobility capacitant feature up. But just to show graphically how the speed changes. So if you now have the OECT and you change the gate bias voltage from -5 to -6 over time, if you only have the neat material, you see the device is far too slow actually to follow the gate bias. However, once we add actually the block copolymer, and again, I'm sure we can actually get even better, it really nicely, the source drain to the off current really follows nicely the gate bias we apply. And I have to see how your time, I think I'm still fine. There is a sweet spot. Clearly, so far I showed data on 25 weight%. If you now take this mobility capacitance product and the threshold voltage shift, so hysteresis, you see we can actually get a good compromise between mobility capacitance and actually hardly any hysteresis between the 25 weight% to 20 to like 30 weight% really. And we still have to understand actually why is it this specific blend composition. So generally, why is this blending approach important? Clearly, I showed it makes really device production and actually the device behavior more reliable, more robust, and more reproducible, independent really from geometry. But I also really like to highlight, and I think that will help here in specs, it opens material space. And just to give an extreme example, again, chemist and in particular says there, P3HD. So we made actually a comparison and made a OECT with P3HD, again in aqueous solution. And you see whatever we do, so we apply different gate biases, you have zero modulation of your source strain, which is not surprising. It really just doesn't work. But once we do the blends, I would not call them super nice OECTs, but you see, once we do blends, we can actually get P3HD working in a aqueous sodium chloride electrolyte. So that really gives hope that we may not always have to go to redesign a lot of the polymers, but can stick to, for initial fundamental studies, to a nice series. And hopefully we can really use this for specs, having one batch that maybe even we can buy to do certain experiments. Clearly then based on that, Seth, we keep you in the business. We will need then, I'm sure, different polymer derivatives. But as mentioned, first you, yes, yes, of course.
It seems a little weird, but it's not inconceivable to me that blending this polymer with N2200.
I come there. Look.
Okay, so it's the same polymer.
Yes, and I brought that in because Antonio Facchetti joined us, as many of you know, who of course used the N2200 very, very early on in his company. And I think it would be nice, like you said, because these materials are around. I have to check actually with him and simply see, you know, actually when we think of compatibilization, to learn is what is this P4HD block in the additive doing? Can we learn by expanding, let's say, this unit here in the 2200, or what happens when we change the side chains that also should affect the mixing entropy and in particular. So, and here's other materials. I think they're possibly, I would put them as definitely plan B. But here he has different hetero interactions, which actually users will know better, will help actually to stiffen the backbone, so prevent rotations, which in my opinion should actually reduce the compatibility with additives. But well, we have to wait and see, and in particular see actually what materials he has around. But that's why I like that in specs we actually deal with N2200, and it potentially can help us understanding the effect of those additives. And I see I have 10 minutes. Let's see where we get. So,
Natalie, can I ask a question before you move on to the next section? For those derivatives, is that, you know, something we should be thinking about as a team? Do we have a lot access? Could we have a lot access to a good amount of that, or would we be very limited in getting that?
Elisa, I have to check. I actually once talked to Antonio. Some are available at larger quantities, some are at lower.
That would be great to know.
Check which ones are available.
Yeah, because then we can start really planning about that. Thank you.
Absolutely, absolutely. But some were done in his company, so I would assume they're here in larger quantities, but yeah, I definitely will check. Good. Now let's go to one of the other objectives, and I definitely keep track of time. Erin, how much time is left for questions, or is it planned that people like Seth, you know, just ask the questions during the talk? So I still have full 10 minutes, or shall I do 5 minutes?
Let's do 5 minutes. I think Erin had to jump off for a family thing.
Ah, okay. Good.
But I want to make sure we get
Lisa.
open questions.
Great. So I stick. So I had 3 topics. I stick now to 2. So let's have a look. How can we really learn about the polymer electrolyte interfaces, which I think is really a very difficult objective. And again, I bore you with P3HD, again, simply because actually we know this material. And rather than have liquid electrolytes, we started actually very early on, and that was before specs, trying to learn about interfaces having another polymers, so we can investigate interfaces in the solid state that helps with microstructure characterization, etc. But we use PVDF because you have fluorines and here you have hydrogens. So if you actually have this arrangement of the chain at room temperature plus minus, you have actually a much higher dielectric constant. So it sort of mimics to a certain extent polymer environment in electrolyte, where the electrolyte will increase the dielectric the dielectric environment. Clearly, again, when we have polymer-polymer blends, we have first, rather than just random mixing, learn a bit about the system. And we usually start with viscosity measurements. So Henry is here. It's pretty simple. We have a viscometer, and we do that for P3HD as PVDF. And we change the molecular weight, again, another reason to have P3HD, and see how the viscosity in 0.1 weight% solutions in chlorobenzene changes. And you see you have an inflection point, and that's the point where we hit the critical molecular weight where you start to have entanglements, knots, like in the hair. And that means here in this area, you have much less diffusion, so mass transport is much lower. And we really call high molecular weight materials once they have reached this critical molecular weight. These guys we call low molecular weight. And once you go blending, this is really important. If you change the molecular weight from 60 kilogram per mole for P3HD and relatively low molecular weight for PVDF, you see the two polymers massively phase separate. So these bright areas is P3HD rich, the dark area here is PVDF rich, this dark here is the substrate. Once we change though to molecular weights where both of the materials are above MC, you see we get pretty homogeneous films. So it's this region over here. If people come from polymer area, the first thing you think this is counterintuitive, because usually people always say the higher the molecular weight of polymers, they actually phase separate. But the thing is we process from solution. And actually, somehow I lost here the molecules. In case you have low molecular weights, they're like little macaroni sticks, not intertwined with each other. So high mass transport, and the high mass transport leads to phase separation. Once you have, imagine here, cooked spaghettis of two colors, they actually really have a lot of knots. I'm not sure why I lost those graphics. And then you get really this nice intermixing. And you really immediately see solutions are where you have one co-solvent. It's really critical. If you measure thermal analysis, you observe an exotherm, meaning at the beginning, you had actually something pretty amorphous, molecular disordered, but intermixed. In the melt, you see this didn't happen. So it means you have already phase separation, and they lead to these two endotherms, the melting of PVDF and melting of P3HD. And here you see the PVDF is here, this dark black layer, P3HD rich is on top. Why is this important? As for specs, actually having this amorphous intermixed phase, we can really influence the local environment. So as mentioned, PVDF can have either the fluorines up and down. So this one is an apolar phase, or you can have the beta phase, which is polar, where all fullerene, I'm not sure why it's red, it should be green, are on one side. So you have actually a dipole from plus to minus. And when we blend it, you see the PVDF here, the characteristics in X-ray diffraction, the more P3HD we add, the more beta phase we have with respect to the alpha phase. So blending definitely has an effect on the materials, and we see that also optically. So simple photoluminescence and absorption spectra. In absorption, you see the 001 transition goes up. In PL massively increases once you blend. It's pretty universal, whatever polymer we use. So this is another thiophene derivative. PL goes up. 00 goes up, and I will not go here into detail, but I can show even with 2D NMR done with Mangiaretti in Lille, we actually start, when you compare the P3HD with the blend, there are new interactions in 2D in NMR, new signals in 2D NMR. And they show that we have very close interactions between P3HD and PVDF. So we can mimic, at least to a certain extent, the environment as in a liquid electrolyte. And again, here we start to continue blending using, rather than PVDF, ionic liquids, etc., where we saw similar things. But with that, I think I should end. Let me see. That was the wrong thing. Oops. Here, that's my last slide. So I hope that really learning about transport on very well-defined systems will help us. And I have to say, it will. I'm not sure about transfer, but I think so too. When we really see whether we have molecular mixing or not, that will allow us to create systems where we also can study transfer. I hope I showed you also that definitely durability can be helped by simple approaches that we as material scientists use. And I see we have 2 minutes left, but I'm happy to answer questions if people are happy to hang in there.
Thanks, Natalie. Spencer, go ahead.
Hi, can you hear me?
Yes.
Okay. So I am not a material scientist or a polymer chemist, but I took one polymer class, and I remember that mixing of polymers is very much a thermodynamic process that can be sometimes tricky to tune. So my question is, do you have to worry about these polymer blends demixing over time because of, like, I don't know, it not being favorable thermodynamically, or is that not really a consideration?
It's not a problem in our case because we trick thermodynamics. And let me see if can you see my slides again?
Yes.
Let me, voila. And that has really to do with the entanglements. And it's a pity that my graphics got lost, but if you just take this, so once you go from the critical molecular weight, let me get this bar down again, to here, and these molecular weight regimes, you really have a lot of entanglements. So if you would melt, actually that would do the opposite effect. So the P3HD would be really entangled with itself, the PVDF would be entangled with itself, and they will never interact because also there's no driving force, nor enthalpic, nor entropic. You know, they're already very disordered, entropy is high, there's no driving force for them to actually mix. But now, because we have the co-solvent, and it's a shame that I lost, you know, these vials, now we have a solvent, and the solvent likes both the P3HD and the PVDF. Therefore, the choice of solvent is really important. That means in solution, the PVDF and the P3HD entangled with each other. So the chains, you know, rather than expulsing themselves, it's really like mechanically interlocking between P3HD and PVDF. And once you cast the film, therefore, actually, they don't phase separate. And Henry can actually say, contrary to what I thought, even when we went and heated the material up, actually, we couldn't see demixing, phase separation. So we really had to go to the melt to then actually demix these type of films. So I really think, especially when you have super high molecular weight, like the 160, 110 mix, or like 130.
And you want one of those chests that we have in the storage locker. Sorry, Natalie, that was me. My microphone clicked open.
Okay. Yeah. So back to Spencer. Yeah, therefore, actually, they're pretty metastable. So it will be very difficult to really phase separate. And because kinetics and these mechanical interlocks, entanglements, keep the two polymers together.
Very cool. Thank you.
Yeah, that's the beauty of it, actually. Yeah.
Thanks.
Actually,
And maybe
Natalie,
Henry can
on that
show
note,
you those schematics with the polymer chains in there again. I have to know.
Natalie, Henry's already done that. He shared it in the chat. So thank you, Henry.
Ah, good. Ah, super. Thank you, Henry.
Natalie, on that note, since you mentioned if you take it to the melt, they phase separate. Do you think they might phase separate if they stay in electrolyte, swollen electrolyte long enough because it sort of plasticizes the chains?
I think plasticization is not good enough because even here, I actually was angry with Henry. Because he wanted immediately to go to the melt to phase separate. And I said, no, don't worry. Once you get here to this cold crystallization peak, it will be fine. Henry should have bet with me. It was not fine. So I think plasticization will not be sufficient. That's something we have to prove. It's actually a very good point. We should do the DSCs after, but I really do not think it will be strong enough, especially when you have the high molecular weight blends. But I guess we put it to the to-do list of Henry. But I'm now here happy to bet that it will not actually help disentangle the films.
Yeah, I was going to add to that I guess kind of what we see is, I think it's more an aggregation effect, right? That when you add the PVDF, we're affecting the nature of the P3HC aggregates, which I think those potentially are more stable than that of when, even if you go above the cold crystallization temperature, you have not yet disrupted that aggregate that you formed from the solid state.
So I want to be, if people need to jump off, I need to jump off, but it looks like Gary has a question. I don't know if Natalie still have a few minutes, but if people need to leave, feel free to jump off.
I have minutes and it was me going late, so I'm happy to answer those questions.
Thanks, Natalie. This was great.
Yeah, sorry for overrunning. I blame my internet.
Okay, Natalie, I have a question for you that I kind of tried to get Alberto to answer in the background so I didn't sound silly. But when you measure the mobility measurements in an OECT, what are you measuring the mobility of?
That's a good question. And actually here I refer to Alberto. I'm really not sure, actually.
What, okay, Albert,
I think it's the holes, because you reduce or oxidize the backbone and create then the electronic charges, and those you move. But I'm not sure if that's very simplistic thinking. So I'm curious what Alberto says.
I guess, what do you mean by what are you measuring the mobility of, Gary?
Well,
I guess it's for the mu C star product. Is that correct, Gary?
Yeah. I saw that in your slides, and I thought, well, I just latched on to the mobility part of it. So the question is when the current flows from source to drain, are you limited by the mobility of one of the charges in the polymer, or are you dragging the electrolyte around as well? That's kind of where I'm going with the questions in the background and what I'm asking here.
So first of all, my understanding is you're measuring the mobility of the electronic charges exclusively because you are measuring a DC current. So you don't have the ambiguity of when you do AC measurements. Now, what you're doing is you're measuring the current and attributing that current to a certain charge density that, at least in principle, you can say you know. So it's the average mobility of the carriers. To your point of you're dragging the electrolyte or not, I guess you could imagine some carriers are completely trapped, some carriers are mobile, you're just measuring the average of all those. And so the effect of the electrolyte would probably manifest itself in the distribution of the mobilities if you were able to disentangle that somehow. You'd see that maybe in some regions of the polymer, the electrolyte limits the mobility, and so maybe those carriers are trapped. In other regions it's not. But the bottom line is that you're measuring the average mobility of all your carriers.
And so does the electrolyte have any role to play at all, other than being part of the injecting the charges into the polymer in the first place? And in which case, I'm sort of struggling here. You can tell me to shut up, but I'm not understanding if the full role of the electrolyte, and I'm not understanding the full role of the electrolyte, especially when you start blending, as Natalie was doing, with polymers that can allow that electrolyte to penetrate. I can see what's happening there, but I just don't understand why we're just ignoring the ions that are moving around. They will try to move as well, and what they are will depend.
I agree, and they would probably do something to the mobility. An analogy maybe could be, there is a very nice experiment that was done. Maybe I'll dig out the paper. This was in field effect transistors. What is called, I can't remember, it was called the Fröhlich effect or something like that, where depending on the dielectric, you got different mobilities because you're polarizing a dielectric under the charge, and you're carrying not only your polaron in the semiconductor, but the polarization in the dielectric with you.
Right.
So
I think that's the direction
like that happening here.
Yeah, and I think that's where then actually the blends like PVDF come in, because indeed, in principle, it should be only the electronic charge carriers. But of course, you change the environment because you get the electrolytes in, you likely change, that was in my third part, which I didn't have time, the chain conformation, especially when you have flexible chain conjugated polymers, maybe the rigid ones not. That's why like Antonio's series on the N2200. So the ions do a lot of things, change of conformation, change the dielectric environment, and that must have an effect on the electronic charge transport, or at least can, let's put it like that. So and therefore, I think these are really, I think that's why specs really is needed, because you can't simply like delineate that easily. I'm curious what Alberto thinks.
So I put the Fröhlich polaron paper in the chat, and I think one of the reasons you say, why are we ignoring it, is that because more often than not, we're using sodium chloride as an electrolyte. So I guess it's always the same electrolyte for everyone. But if you started playing around with the counter ion, you'd probably see some of these effects show up. And that's actually a very good point, and it would be an interesting experiment. To the 0th degree, we want to see this by mid-IR spectroscopy to see if we can tell whether the counter ion changes the delocalization of the charge. But that's not really what you're asking here. You're asking not only the delocalization, but when the charge moves, what does it drag with it, which is an even more complicated question.
I did not think that sodium chloride was the electrolyte.
Wow. Can I add here? So first of all, usually the mobility of ions is many order of magnitude smaller than of electrons and holes. And regarding what they do, actually there are a couple of models of coupled equations for electrons and ions. So it's more what Alberto said. They basically change the potential and the electric field and the distribution in the field.
That's true that they're very different, independent of each other. But if the charge on the polymer is strongly coupled to an ion in the solution, and as you try to move the ion in the polymer, you're going to have to drag the ion in the solution as well. That's the picture I'm trying to understand. So
and I think this is really the third objective, no, sort of.
Yes, that's why I'm trying to balance making a contribution with ignorance here. So that's kind of I'm just trying to understand. If the sodium chloride is the electrolyte, then I think my question is mute. But if it's something else, like a standard electrolyte, like ammonium tetrafluoroborate or something like that, then it's going to matter.
Yeah, maybe we should think what would be an extreme electrolyte, because actually what surprised me with the P3HD PVDF transistors, Alberto knows there is this old paper of Henning and Davisia people still at that time on normal thin film transistors that showed if you had superpolar, highly polar gate dielectrics, charges got trapped. So there we didn't even talk about ions. So the transistors performance, the thin film transistor performance went down. Yeah. But in our blends, we could actually make pretty well behaving P3HD PVDF thin film transistors, which sort of speaks and against the, that there were some interactions. But I think with ion, of course, I'm sure that will. So if you get ions that we expect to really do something, we should actually start studying that. So yeah, I really think of all the 3 objectives, this one, the last one, I really think it will be good for us, but it will be challenging. That's why I didn't talk about it.
So if you push, if the concept of specs is to push this so that the electrons and holes can do reduction and oxidation chemistry, then we do have to start worrying about the mobility of those entities into the polymer film. But the way you're talking about it is if all we have to worry about is the charges on the polymer chain and what they're doing.
Actually, what I showed was nearly the opposite. Actually, I sort of ignored what happens once the ions are in and you get current. But I think a lot of the blending, in my opinion, helps to get the ions to the backbone.
Okay.
Yeah.
It gets them.
Oxidizes and creates the charges, but we have, at least in my opinion, we do not have information on the ion-polaron interactions. We simply see that, we reduce hysteresis, but I really think that has to do with how fast the ions can get in and out. So it's only the first step that we solved. But the key thing about ion-polaron interactions, I don't think our data shows anything actually.
Yeah, we got a disagreement between what Alberto says and Neil here, in that Neil is saying that at DC biases you'll see lots of ion transport. It seems that Can you expand, Neil? You've been ominously quiet. Your microphone's not working. I can see your lips moving and I can't hear you. It's that special thing that your wife has for you.
Yeah. How about now?
Yeah. That's
Can
good.
you hear? All right.
Yeah.
Yeah. From an electrochemical point of view, I don't think you need to discharge the ions at the 2 electrodes. I think that just moving them from one side to the other is sufficient to create current. Now, once the system, it's basically the principle of a supercapacitor. Once the system is fully charged, where you've moved the ions as far as possible, which is going to take some time, the current flow will then drop. But I would be doing electrochemical impedance on these, and maybe that's been done, where at high modulation frequencies, the ions won't be able to keep up with the modulation, but the electrons will. And then you can separate out the ion movement versus the electronic movement.
I think
like
what
that
you're saying
idea.
about the charging as a capacitor, that's what we see. So if we measure the gate current during the charging of a transistor, that's when we'll see the ionic contribution. Once a transistor is charged and the charges are in the channel, I don't think you would see any of that as you run the transistor in DC.
So the charges are by that time fixed in the channel in position.
That's how I picture it. Yeah.
You might be right. It's been a long time since I've thought about this. Once the double layers are set up against the source and the drain contacts, maybe they don't change. Maybe the ion movement that I'm thinking about occurs so quickly when you guys make the devices and connect them for the first time that
if you measure the gate current when you first charge up the transistor, you see those transients, like the capacitor transients.
Okay. So you moved the ions to their permanent position.
I think so, yeah.
Now they're fixed. Okay. Yeah, you're right. But if they do discharge at the electrodes, then you're in big trouble.
And
then you'll
and the capacitive, sorry, the displacement currents, you only see them near the electrodes, right? 'Cause
Yeah,
it's the displacement in the metal. Yeah, so
right.
whatever happens in the channel with the ions, you wouldn't be able to see. 'Cause that's
Okay, so
the
you
metal
you
electrode.
basically charged the capacitor. Those charges are now fixed, and any changes that you see on top of that must be electronic.
That's how I picture
transfer.
it. Yeah.
Okay, I hope you're right. I think you probably are. I haven't worked on FETs for about 20 years, so and we tried when we were doing this, we were trying to avoid ions at all costs. And so I haven't really thought deeply about this. Well, I have to say though, Natalie, I'm really intrigued by this blending concept, and I put some stuff in the chat.
Okay. Can somebody download the chat because I can't see it currently, or maybe I can get off.
Yeah, I don't know whether that's part.
I think
part
my
of the
students maybe
recording
are still there. Maybe they can.
Yeah. So I had a question. If you back when you first did the blending with an OPV donor acceptor blend, I was intrigued by those results because when you account for dilution, it looked like you were getting the same net photocurrent. So that tells me that the donor acceptor blend is essentially retained in its properties, even though you've added this host polymer to mechanically strengthen that. Is that right?
And it is actually, yes, because we did the phase diagrams. I should have maybe put it in. It's a ternary phase diagram. And you see that the polyethylene, but actually that's nearly intuitive, I mean, it's carbon high. I mean, nothing really interacts with polyethylene, only Teflon is worse interaction. So it was not really surprising, but actually the phase diagram definitely shows it's really just sitting there and helps with mechanical robustness, reducing traps, because we really think it prevents humidity to go in, but it doesn't affect the ordering. But therefore, the processing is so important.
Absolutely.
You really have to have the P3HD, PCBM essentially solidify first. And that's why they sort of behave the same. And then the polyethylene.
So you guys haven't tried this?
Pardon?
You haven't tried this with one of the modern donor acceptor blends that produce these high efficiencies OPVs?
No, but actually it's on my to-do list now that Antonio is here.
Yeah,
and actually there I would not even go for polyethylene, but really the ultramolecular weight polystyrene. So we have actually structural analysis with Kitty Frey on PC11 PCBM, but we really should go once for the new donor acceptor stuff. But I'm not really a solar cell device person, so I never was like, but yeah, we will do it, especially when you think we should.
Yeah, that could be an interesting strategy to, if that works, then to sneak in catalytic sites and things of that sort in the host without having to modify the OPV donor acceptor blend.
Yes, because I also talked to Erin, but I didn't want to convolute this actually too much. Erin really said I should focus on transport, because I talked to Ian McCulloch at one of the conferences recently. And I'm curious what Gary says. He said they only needed the nanoparticles approach really to get thick enough films for their hydrogen production work. So it had nothing to do with anything else, because he said, because I asked, does the device depend on particle size or whatever? And he said, no, once you swell it with the electrolyte, essentially, I mean, the particles are so swollen, you don't really have interfaces anymore. So they really just use it working from a dispersion to get to thick films. And then I thought, well, I mean, we know how to make thick films. But again, I'm not really the hydrogen production person, but it's something to keep in mind, and we should try, in my opinion.
Yeah. It would be brand new. Exactly the kind of stuff that DOE wants us to work on.
Yeah. So actually, if Gary and Obadiah, because you worked on particles, Gary, can once tell us what systems you used? We can give it a try. I'm not sure if Gary still is there.
Yeah, I'm still here. I'm still here. No, we only use the same system that that Ian used originally, which and of course it has a sacrificial reductant of ascorbic acid in the system. So I can't remember what the polymer was. What was it, Obadiah? It was the one that has two names. PM.
It was PDB7TH with THI-TBR as the acceptor.
Yeah, I reach out. Maybe if you can give us the complete recipe, we can give it a try. And again, maybe not polyethylene, but either polystyrene or even better, possibly PMMA, because it's more polar and comes in high molecular weight.
Well, actually, Natalie, one of the things we did try, I think, Obadiah may correct me on this, but when we had nanoparticles that we wanted to move into a non-aqueous environment, we tried your ultra high molecular weight polystyrene as a binding agent, and I don't think that was very successful. But I'm not sure why that was. So we have kind of dabbled, but
I'm not 100% sure Max actually tried that. We would have to circle back with them.
So that's how much
maybe
we did. We
try,
did dabble.
we can maybe give a first try. Yeah, because I think Henry definitely also worked already with ultra molecular weight polystyrene. I'm not sure, it's a beast. I mean, polyethylene is worst, but there's not much margins how to dissolve it and process it. So I think, if you give us guidance, we can give a quick, well, maybe not so quick try and take it from there.
Yeah, I mean, we can certainly provide a very complete recipe. Max has been very careful about documenting and really being sure that everything works the way it's supposed to. So,
yeah, great. I think I slowly now have to leave, but it's self-inflicted. Any other urgent questions? If Henry or so are still here, I don't know if you can make me a copy of the chat. That would be great.
Yeah, I'll send it to you. I downloaded it.
I think Jen can do it because she's. She's
Jen possibly can do it.
Controller.
Yeah, I'll go ahead and download it and share it with everybody along with the video for this.
Okay, that's super. Thank you, Jen.
Sure.
Okie doke. This was fun. So I stop sharing and then maybe I see people so I can say bye. Okie doke. Ciao, ciao. Alberto, I guess I see you later at 5 my time.
Yep.
Good. I will be there. Ciao, ciao.
Hopefully
ciao,
Italy will have qualified for the Euro by then.
Oh, the football?
Yeah, we're playing Ukraine at noon.
Oh, what about Switzerland?
Switzerland is through already, I think.
Yeah, good. Okay, I keep